On the morning of November 20th, 1980, Lake Peigneur was about 10 feet deep. By nightfall, it was hundreds. Everyone survived. The rig crew, the 50-plus miners underground. But 11 barges, a tugboat, drilling rigs, trees, and part of Jefferson Island were gone. How does a lake fall into the ground? It starts with a 14-inch drill bit and a map that was wrong. Lake Peigneur, set in Iberia Parish, Louisiana, was once a shallow freshwater lake. Its surface stretched across about 1,300 acres, with an average depth of just 3 meters, or roughly 10 feet. The water was clear enough to see the bottom in places, and the lake's edge was lined with live oaks and greenhouses from the gardens on Jefferson Island. Beneath this calm surface lay a massive salt dome, a geological pillar that had been mined for decades. The Diamond Crystal Salt Company's mine followed a room and pillar layout, with a grid of tunnels and thick columns of salt supporting the ceiling. The mine extended down to depths of nearly 300 meters, or about 1,000 feet, directly below the lake. On November 20th, 1980, that entire stack of lake, dome, mine and drilling rig came undone. By evening, the lake was unrecognizable, a deep basin filled with brackish water, hundreds of feet deep in places, and the original shoreline had shifted inward by more than 60 acres. The transformation was total, yet every person on site survived. More than 50 miners underground escaped through the main shaft, and the drilling crew evacuated by boat before the worst began. No lives were lost. The physical losses were stark and exact. 2 drilling rigs vanished, 11 barges, a tugboat, a dock, trucks and other vehicles, several greenhouses, mature live oaks, and about 65 acres of Jefferson Island all disappeared into the widening hole. The question remains, how does a lake collapse into itself? The answer begins with a drill bit, a map, and the geometry of what lay hidden below the surface. The origins of the disaster begin far below the surface, in a layer of salt left behind by ancient seas. Over millions of years, this thick band of halite was buried under sand and clay, then slowly pushed upward by the pressure of younger sediments. The result is a salt dome, a column of nearly pure salt, shaped by a process called diapyrism, where the salt rises through the surrounding rock like a slow-motion bubble. Jefferson Island sits atop one of these domes, its highest point about 15 meters or 50 feet above the surrounding wetlands. Inside the dome, miners used a method known as room and pillar. They carved a grid of wide chambers, leaving behind massive pillars of salt to support the roof. These galleries, some more than 100 feet wide, formed a honeycomb that extended nearly 1,000 feet, or 300 meters, below the lake. The salt was extracted for decades, hauled to the surface along tunnels and shafts that wound through the dome's core. Above the salt, a thin layer of sediment separated the mine from the lake. The lake itself was shallow, only about 3 meters deep, with a surface area of more than 5 square kilometers. Floating on this water, oil companies set up drilling rigs, supported by barges and platforms. The drill string, a connected assembly of pipes and tools, reached down through the water, through the soft lake bed, and into the salt dome below. Not all salt mining is mechanical. In some places, water is pumped underground to dissolve the salt, creating brine that is brought back to the surface. This is called solution mining, and it differs from the room and pillar method used at Jefferson Island, where miners physically excavated the salt. The distinction matters. When water meets halite, the salt dissolves rapidly, and the resulting brine can undermine even the thickest pillars if the flow is uncontrolled. The entire system depended on accurate maps, on the boundary between where it was safe to drill and where the mine galleries opened up below. On November 20th, 1980, A single error in that boundary would prove catastrophic. At sunrise on November 20th, 1980, two separate teams began their workday above and below Lake Peigneur. On the surface, the Wilson brothers' crew prepared their drilling rig for Texaco, anchored on a barge near the eastern edge of the lake. The rig's derrick stood about 45 meters, or 150 feet, above the water, and the plan was straightforward. Drill through the sediment and salt dome to reach a target depth of around 400 meters, or 1,300 feet. The morning was quiet, the lake still, and the drilling crew went through routine checks, lowering the drill string section by section. Each length of pipe added a steady rhythm to the operation. Far below, in the galleries of the Diamond Crystal Salt Company mine, more than 50 miners were scattered through the grid of tunnels. Their work was methodical, operating loaders, maintaining ventilation, and inspecting the pillars of salt that supported the ceiling. The mine's lighting cast regular shadows across the white salt walls, and the miners followed familiar paths between extraction points and the main shaft. Communication with the surface was by radio and elevator, with no indication of any unusual hazard. Neither team had reason to suspect that the rig above and the miners below were nearly aligned over one of the mine's active chambers. The separation between them, hundreds of meters of rock and salt, had always been considered a safe barrier. That confidence held until late morning, when the drilling crew noticed resistance at the drill bit. At a depth of about 374 meters, or 1,228 feet, the drill string became stuck. Operations paused as the crew tried to work the pipe free, unaware that this point of contact would soon connect the lake to the labyrinth beneath. The breach began with a single, deliberate action, a 14-inch or 36-centimeter drill bit pressing through the sediment, then the salt, finally breaking into an open gallery of the Diamond Crystal mine. At first, the opening was no larger than the drill itself, but the moment freshwater touched the salt, a chemical process started that could not be reversed. Halite dissolves rapidly in fresh water, more than 350 pounds per cubic foot, so the neat borehole quickly became a widening conduit. Water poured down, dissolving the salt walls and ceiling, and the initial puncture expanded minute by minute. This was not a sudden collapse, but a progressive failure. The mine roof gave way in stages. As the water found new paths, it carved out larger and larger voids, undermining the pillars that once supported hundreds of feet of overburden. The drainage unfolded over several hours. The lake did not vanish in an instant. Instead, its surface lowered as the flow accelerated, then slowed, then surged again as new sections of the mine failed. On the surface, the process revealed itself as a growing vortex. The hydraulic gradient pulled water into the breach with increasing force. The whirlpool's diameter grew from a few meters to over 60 meters, or about 200 feet, in less than half a day. Objects disappeared in a sequence that reflected their position and mass. First the drilling rig itself, then a second rig nearby, followed by 11 barges, a tugboat, the dock, trucks, greenhouses, and finally several acres of Jefferson Island's shoreline and mature live oaks. Each was drawn down not by spectacle, but by the physics of water seeking the lowest available space, enlarging the opening as it went. The transformation was relentless, precise, and entirely mechanical. As the lake finished draining, the aftermath unfolded with a logic that defied ordinary experience. Several of the barges that had vanished into the whirlpool did not remain lost. Over the following hours, as the void beneath Lake Peigneur refilled, air trapped inside the hulls allowed between 5 and 7 of those barges to rise back to the surface. Reports disagree on the exact number, but the spectacle of heavy steel vessels bobbing up after being swallowed was confirmed by engineers and news crews alike. Meanwhile, the Delcambre Canal, which once carried water out to Vermilion Bay, reversed its direction. For about an hour, Gulf water surged backward, pouring through the canal and into the empty basin. This created a temporary waterfall, measured by surveyors at roughly 30 to 40 feet, about 9 to 12 metres, tumbling into the new sinkhole. When the flow finally stabilised, Lake Peigneur was no longer a shallow, clear freshwater lake. In its place stood a deep, brackish body of water, permanently changed in both depth and chemistry. Responsibility for the disaster at Lake Peigneur settled into a triangle of companies, each with its own account of the events. The Diamond Crystal Salt Company managed the underground mine. Texaco commissioned the drilling operation above. The Wilson brothers' crew handled the rig itself. When the breach occurred, all three faced questions about how the rig came to be positioned over an active mine chamber. The heart of the dispute lay in the maps. Two surveys, one from Diamond Crystal and one from Texaco, showed different boundaries. The Diamond Crystal survey placed the rig safely outside the mine's edge, while Texaco's map, built on a different coordinate system, put the drill directly above a mined-out gallery. The conversion between mapping systems became a source of controversy. Some reports blame a projection error, others point to missing or misinterpreted mine records. In the aftermath, litigation began almost immediately. Settlement figures in the public record range from $32 million to over $200 million in claims, though the final out-of-court agreement in 1983 is most often cited at $32 million, with Texaco paying the majority. The physical evidence needed for a definitive answer, the breached mine roof and the precise drill entry point, was destroyed in the collapse and inundation. With the mine flooded and the rig site now under deep water, no conclusive forensic reconstruction was possible. The true origin of the mapping error remains uncertain, preserved only in the fragments of lost documents and contested memories. The mine is gone, the lake is deeper, and the records remain incomplete. Today, new wells still tap domes mapped in 2 dimensions, beneath towns and fields. When engineering meets geology, the margin for error is narrow, and the evidence sometimes vanishes into the void it leaves behind.